Week 9 lecture on Tuesday. So for the agenda for today, we're going to do more examples on thin wall analysis, and then we're going to go into a new subtopic, which is longitudinal shear. We're not going to learn any new formulas, but it's more of an analysis, okay? Longitudinal shear, there's one extra formula, but it's not very difficult. Okay, now let's look at this example. But before we go to this example, I want to refresh your memory on thin wall analysis. Okay, as you can see, example 1 is a thin wall structure. So a few things to consider doing thin wall analysis is the design of shear flow, which is Q, is critical. Okay. The next thing that we learn is the terminal has zero shear flow or shear stress. A very distinct about thin wall analysis, it can be either a box beam. In this case, you have 2Q, or it can be a wide flange, which we only use, which is only Q. And then the next thing that we learn is the shear flow will flow outwards from the terminal above the, not above or on the side of the shear force relative to the geometric centroid. And the most critical one, we already know the thickness T is perpendicular to the shear flow vector. Okay, so just to quickly recap, and this is why I picked this problem. It's a very unique and interesting problem. So this problem states that a shear force V at 18 kilonewton is applied to the symmetry box girder. Determine the shear flow at points A, okay, and B. A is straightforward. B is a, you have to is a bit of conceptual question, which is not difficult if you apply the rules that I teach you guys. Okay, now let's start. Okay, so I'm not going to determine so let's do the transformation first. So we know that this is our x, okay, this will be our y, and this is our z. Okay, so that is our transformation. So we know that there's a force coming down, a shear force coming down, right, Vy, and it is 18 times 10 to the power 3 Newton. I'm not going to waste time finding second moment of area. I'm just going to write it down. So IZZ will be equal to 125.166 times 10 to the power minus 6 meter 4. And we know where the geometric centroid is because it's axis symmetry. So I'm going to sketch our geometric centroid. And this is our geometric centroid. So this is over here, our geometric centroid. So to solve this problem, as I mentioned earlier, is how we design the shear flow. Okay, once you design the shear flow correctly to determine those values, the shear flow at point A and point B are very straightforward. Okay, so let's look at this. Okay, so I'm going to sketch points on the structure. So we have not to scale, okay. One here. We got another one. Okay, so this is our flanges. Then we have our webs. Then we have another web. And I deliberately stopped drawing there because over here, this is our geometric centroid. So this is, again, I'll write it down, geometric centroid. Right. So if you see how this thing flow, right? I'm going to do this. I'm going to copy. Okay. And I'm going to do it again. Right. So this is over here is given to us that this is our point A. And over here, this is our point B. Okay, so those are given to us. So we are aware that over here, this is where our By comes. So we know that this is a box beam design. Okay. So another rule that I forgot to wrote down here, the major web. Remember, major web controls the Q direction, right? So we're going to design our shear flow on a major web, and a major web are the two vertical web. So I'll label this as our, so this and this are our major web. So we design our shear flow, it will be coming down this way. Right? So we know over here, this is our terminal. Okay, so this is our T1, represent terminal. Right? So we will also think, okay, so there's A at point A, okay, At point B, we have another flange. Okay, so some of us will think, okay, if point B there's a flange over there, you want to think that the fluid or the shear flow is like fluid, like I mentioned earlier, right? It will be flowing inwards. And once it flow inwards, when it meet one another, it has nowhere to go. Okay, when it has nowhere to go, it's a terminal. So down here is our terminal 2. Okay, so you can design it this way, right? Or if you follow the rules, right? It states the rules over here. It states that the shear flow will flow outwards from the terminal on the side of the shear flow relative to the geometric centroid. So what I like to do is matter of preference. The answer will still be the same. I'll still design the shear flow. Okay. So this is our terminal 1. And we know over here, this is our terminal 2, right? Because how do we know? Because from this analysis, we know there's our terminal 2 because both of them meeting one another. You can push it outwards also. Does not matter whether it's inwards or outwards. Your mathematical form will still be the same. So the shear flow at T1 is equal to 0. The shear flow at T2 will also be equal to what? 0. Okay. So when you do the math to calculate the first moment of area, it's always relative from the terminal. Yes or no? Right? It's all relative from the terminal. Okay. I think I'm going to do a quick way or just to revise how to calculate the first moment of area with your first, then we at point A, then we do point B. Okay, so I'm going to get this geometry down. Ah, I forgot, did I record? Ah, I did. Okay. So we're going to deal with point A. Okay. So we already know how the shear flow has been designed. So terminal A, we know is box beam. The area that we're going to consider this entire area under box beam analysis. Okay. So relative from the terminal. Okay. So we're going to do with point A. And we know there is a box beam. And it's going to be Q 2Q, right? So from here, we find our I'm going to draw our transformation first. So this is our X, Y, and Z. So our first moment of area about the Z-axis. So with depth Y bar. So the Z-axis, so this is our width. Over here, this is our depth. So the width will be equal to 125. The depth is 10 millimeters. The Y bar will be 150 minus by 10 divided by 2. Okay, we know this is the values because we know the first moment of area to consider, and the first moment of area to consider is controlled by the shear flow. Okay, by design of the shear flow. So from here, this will be equal to 150 minus 10 divided by 2 times 10 times 125 is equal to 181.25. times 10 to the power 3 millimeter cube. So this is also equal to 181.25 times 10 to the power minus